Welcome and thank you for joining us today. My name is Laura Ramos and here with me my colleague Carmen Fury. We are both application engineers at Monolithic Power Systems. Carmen will be presenting this webinar. So let's get started with the presentation and turning over to Carmen.
Thank you, Laura, and thank you all for joining us today. I'm Carmine Fiore, and I work at MPS as an application engineer for motor and sensor products. Besides Laura, today with me I have two other MPS colleagues, Marco Hepp, Business Development Manager for Sensor Products, working for Central Europe, and Florian Dubon-Girard, Field Application Engineer, also for Central Europe area. Today's webinar, we will first talk about position sensors and then about current sensors. In both cases, we will analyze the benefits of magnetic sensing and then which technology is used in MPS sensors. Then we will move on to review some of the applications where our sensors can be used. At the end of the webinar, there will be a live demonstration and a Q&A session. So let's start with position sensors. And by seeing what are the benefits of magnetic angular position sensing compared to alternatives like optical encoders and potentiometers. The main benefits of this technology are a higher durability due to the absence of contact between moving parts, the immunity to the effect of some external agents like dust and oil, robustness to shock and vibration, and finally, a low power consumption. MPS sensors use a specific technology that gives them an edge over competitor products. This technology consists in sampling the intensity of the magnetic field in a full rotation, detect where the maximum intensity is located, and from this information, obtain the direction of the magnetic field. This technique allows to obtain a faster measurement and requires less silicon area compared to a more usual technique consisting in measuring the magnetic field intensity along two directions, perpendicular directions, and then obtaining the angle by calculating the arc tangent. MPS MagAlpha family is composed of a wide range of products who share some common features. For example, they support different geometrical configurations, as you can see in the pictures on the right. They have a fast angle sampling of 1 microsecond, a wide magnetic field range, a configurable zero, and finally, they can detect the intensity of the magnetic field. This chart shows the MagAlpha sensors portfolio. MagAlpha sensors are suitable for motor, encoder, and HMI applications. Some sensors have also the automotive grade qualification. We will check every application in more detail in the next slide. So, for general encoder applications, we have a group of ICs with SPI, SSI, ABZ, and PWM interfaces. All MagAlpha sensors have an internal low-pass filter to stabilize the angle reading. The maximum output resolution of each IC depends on the bandwidth frequency of this filter. At a high cutoff, at a high bandwidth frequency, we have a faster response to an angle change, but also a lower resolution due to a higher noise. Obviously, with a low frequency, we have a higher resolution, but a worse dynamic performance. For some sensors, this frequency is fixed. So the IC has to be chosen carefully based on the application. On the other hand, we also provide the MA732 where the bandwidth can be adjusted, providing extra flexibility to better assess what is the best configuration for the application. Finally, in this group, we also have the MA710 that can work with very low magnetic fields down to 15 millitesla. The low power sensors are able to support an idle state where everything except the SPI peripheral is shut down in the IC. This lowers the power consumption down to 1 microampere. The idle state activation can be controlled in several ways, both by internal register setting and by external signals. Currently, there are two low-power ICs that only differ in the package. So we have the MA780 with a QFN 16 3x3 package, and the MA782 with a QFN 14 2x2 millimeters package. Let's move on now to the motor control ICs. These ICs provide an UVW output to emulate the output of 3-hole sensors. Also in this case, there are parts with a fixed internal filter bandwidth and one with a configurable bandwidth. Moreover, the MA102 provides a differential UVW output. The HMI sensors are the simplest ones of the family, and they all provide an SPI interface plus an extra interface that differs from IC to IC. So we have the SSI for the MA800, ABZ for the MA820, and PWM for the MA850. The resolution of these ICs is lower compared to the other the ICs for the other application that we have seen. This is due to the lower specs that we usually have in this kind of application. Finally, we have automotive grade sensors. Each one of these sensors has the same features as some of the ICs that we have seen in the previous slides. The only thing that the things that they have, the extra features that they have are a QFN 16 3x3 millimeters package with wettable flanks and obviously an ACQ100 grade 1 qualification. MPS provides different tools to evaluate the performance of our sensors. We have evaluation boards available in different form factors that can be connected to a PC via a communication kit, which in turn allows to use the make-on map to configure and test the sensors. We will show how to use one of the evaluation boards and the make-on map during the live demonstration. To conclude this part, we also mentioned that MPS provides magnets that can be used together with our sensors. These magnets come in different shapes and dimensions to better adapt to different applications. Let's now move on to the current sensors. In this case, magnetic current sensing has some benefits compared to other technologies. For example, compared to shunt resistors, magnetic sensing guarantees a better efficiency and voltage isolation, while compared to transformers, it allows to measure both AC and DC currents and also requires less space. MPS current sensors are based on the Hall effect principle. The current flowing inside the sensor generates a magnetic field, and this magnetic field is sensed internally in the IC. This technology provides a very efficient measurement due to the low resistance of the current path. It also provides galvanic isolation and a proportional relationship between the current and the output voltage. The MPS MCS current sensors family is formed by several devices which share some common features like isolated bidirectional current sensing, differential sensing that provides immunity from stray fields, a high accuracy between 2.5% and 3%, and a low current path resistance down to 0.9 milliohms. Finally, we also have a 2.5 kilovolts isolation capacity. The various ICs of this family differ in their supply voltage, that is either 3.3 volts or 5 volts, and finally in the sensing range, going from plus minus 5 amperes to plus minus 50 amperes. Our current sensors can be used both for control and protection purposes. For example, in motor control, the MCS sensors can be used to sense the current both in the motor phases and at the low side MOSFET source to protect the system from short circuits. Another possible application is in solar power systems, where the sensor can be used both on the AC and the DC side of the setup in order to monitor the current intensity and optimize the control parameters of the system. Now we go on to the live demonstration, and I'll give it over to Laura. We'll start with the position sensor.
Thank you, Carmen. Here we have the MPS Node Evaluation Kit. It consists in a PCB with the MPS NA732 sensor and a node with a magnet attached at the bottom of it. The evaluation kit is connected to Carmen's laptop via a communication kit. This arrangement allows us to use the MPS Macom app to read the output sensor in real time and change its settings.
Yeah, now you can see on my screen both the graphical interface provided by MPS, the Macom app, and on the top right corner you can see the knob. So you will see that as soon as Laura starts rotating it, the angle displayed in the interface is changing accordingly. Now, for example, if Laura keeps rotating in a clockwise direction, you can see that it goes in the same direction. But I also have a feature to reverse the rotation direction. So now if I change the configuration, you can see that now Laura is turning counterclockwise, but the angle is changing in the clockwise direction. Between the other features provided by the interface and obviously by the sensor, we have the ability to set a new zero angle. For example, if now I push the button, you will see that the angle has gone to 0. And finally, we have the low magnetic field detection. So if Laura now removes the knob, you can see that there is a flag turning on at the bottom of the GUI that tells us that the sensor is detecting a very low magnetic field. We are over with the magnetic position demo, and we can move on to the current sensor demo.
On this board, we have the MCS 1803GA05 sensor. This sensor has a sensitivity of 400 millivolts per ampere. A 5-power supply provides both the current flowing in the sensing part and the supply voltage for the IC. We will use an electronic load to control the current flowing in the sensing part. The sensor output is connected to a digital multimeter. Currently, the 5 voltage supply is provided to the IC, but there is not current flowing. You can see that the output current is 2.5 volts. Now we are gonna put some current. At 2 current amperes, 2 amperes current is flowing. The sensor output has changed to 3.3 volts. After that, we are gonna change the current direction.
So yeah, you can see that the output changed by 800 millivolts. And you can also notice how we have just a bias error of 5 millivolts in the sensor.
As you can see, after reversing the current, the sensor output has changed to 1.7 volts. Well, that is the demonstration is over. Now we can move on the Q&A section.
Yeah.
Thank you, Carmenia and Laura. So that's time for Q&A. If you have any question, just you can use the button in Zoom to make it, and either Carmenia and Laura or Florian and Marco will try to reply. Is there somebody has any question regarding magnetic sensors, current sensors, applications? Also, as a reminder, as I mentioned before, in future, if you need any question, you can contact us through our website. Also, we have MPS now, so you can contact us and we can do either a customized demo or solve your questions online, so we can connect from our lab. So there is one question regarding current sensors. Any use to measure current from a PSU to a load? Do you have any, so from a power supply to a load, I understand the customer is asking if will be possible to use this isolated current sensor to measure this.
Oh, yes, definitely. This is always a possibility to check and monitor system currents. And with the isolation capability, this could be even a different voltage domain. That means you can definitely use that. Actually, we also see many users asking for current monitoring within the same voltage domain, but with the benefit of being not limited by any ground loops. So we were surprised that there are also users using current sensors in the same voltage domain and not using the isolation, but using the benefit of having an isolated current sensing feature. And this is definitely a possibility. Consider building automation and small PLCs, especially in the dedicated applications where voltages beyond 60 volts can be critical. This is a very, very popular use for monitoring total power supply or subsystem power consumption.
Thank you, Marco. There is another question regarding the application of low power knob in a HMI. What can be the average consumption of the magnetic sensor?
Yeah, that's a very good question, because it's really depending on the application. So if you consider an HMI knob with an update rate of, let's say, 5 Hertz, and this is not too slow to be sensible slowly, yeah. So it's relatively, with 200 milliseconds, relatively fast response possible. 5 Hertz is a popular value. Some choose 10 Hertz, what is very fast for human interface. And in that case, you end up on an 8-bit value in a range of 4 microamps average current. The point here is, as Carmine mentioned, the peak current will be 10 milliamps, but for a very short time. And this duty cycle means for, let's say, 200 milliseconds, just a short power on, and the rest with a less than 1 microamp power off, generates a final 4 microamp average current. It's most of the time it's turned off, and just a short time it's active and on.
Thank you, Marco. Any further questions from our attendees? Taking advantage that we have today here all the specialists in MPS.
One point, if your question might touch some confidential content you don't want to share in a public room, there's always a possibility to contact us directly in a, let's say, in a closed room to discuss your application details. So we understand that not everybody wants to share in public his questions. Even beyond this event or beyond this session, we are available.
Sure. Okay. There is another question regarding angular sensors and the interface. It can be used more than one, like, for example, APZ and SPI at the same time.
Yes, definitely. Very good. Some applications or some sensors on the market have the conflict on accessing one interface and stopping the other interface. We do not have that situation here. All our interfaces are fully working in parallel. That means there is no impact on an SPI or SSI interface to quadrature, PWM, or UVW. They all operate in a full real-time, full parallel, and non vice versa affecting situation. They are all available at the same time. And this is important for motor sensors, where the users like the ABZ and the UVW interface at the same time, connecting a motor with the sensor to a separate drive, for example. Yes, no problems and full parallel use. Good question.
Thank you.